Here we have a geometric sequence. It's a geometric sequence because succeeding items are generated by multiplication rather than addition or subtraction, as was the case with arithmetic sequences. Now the multiplier here is 3 because 2 times 3 gives 6, 6 times 3 is 18, 18 times 3 is 54, and so on. Now this multiplier that's used to generate succeeding terms is called a common ratio. It's the common ratio in this geometric sequence. Now take a look at this pattern. If a sub 1 is 2, that's our first term here, a sub 2 is found by multiplying 2 times that common ratio 3. And then a sub 3 is the previous term times 3, and a sub 4 is the previous term times 3. You see, every time we generate another term, we're just popping in another factor of that common ratio. Now, more symbolically, we think of it like this. The second term has one common ratio. The third term has 2 factors of that common ratio. The fourth term has 3 factors of that common ratio. So we think of it like this. The first term has no factors of the common ratio. Second term has 1 factor of the common ratio, and so on. And so to generate the nth term, you see the expression for the nth term, it would be the first term times the common ratio used as a factor n minus 1 times. You see, we had the n minus 1 involved in the arithmetic sequences before, and now we see it again on our geometric sequences. Well, using this idea, we can generate an expression for the nth term, and we do that like this. Here's the geometric sequence we started with. We know that the first term is 2 and the common ratio is 3. And by the way, if you ever get confused about the value of the common ratio, and sometimes there is confusion because the terms are not as easily read, or you can't see through them as easily as you can here. They might be fractions, for example, and there might be a sign change between them. Well, under those circumstances, just realize that this common ratio can be found by just taking the ratio of succeeding terms like this. We could take 6 divided by 2 is 3. 18 divided by 6. 54 divided by 18. You see, it is a particular term divided by the one that precedes it that gives us this common ratio if we're ever confused about that. Okay, so the nth term is the first term times the common ratio used as a factor n minus 1 times. So here, the a sub 1 is 2. And the common ratio is 3, so it's 3 to the n minus 1. Here's the expression to generate the nth term. We could generate the 20th term, you see, just by replacing n with 20, and we would have the value of the 20th term. All right, let's consider a few problems. Suppose we want to find the 15th term if we know that the first term is 20 and the common ratio is 1.05. Well, we just start with the idea of the nth term. The nth term is the first term times the common ratio raised to the n minus 1 power. Oh, by the way, notice that in certain problems like this, you might see an expression and you might wonder whether or not it's geometric. You might think, well, is this a geometric sequence or an arithmetic sequence or something like that? And it turns out that when we see an expression in which we have a counting mechanism as the exponent on some base, it's the base of that exponent that turns out to be the common ratio. And we saw earlier with the arithmetic sequences that it was the coefficient of the counting mechanism that turned out to be important to us. That was our common difference. Okay, at any rate, let's see. The nth term is, and a sub 1, we're told, is 20. Common ratio is 1.05, and this is to the n minus 1. Now we're just plugging in the information given, but we're asked to find a sub 15. So a sub 15 is found by using our expression here and replacing n with 15. You see, and now we have 1.05 to the 14th. Clearly here we would use the calculator to make the calculation, but be careful in doing that. Don't start with the 20 in making the calculation. 20 is not raised to the 14th power. Only this factor, only the 1.05 is raised to the 14th power. So you might start right here in making the calculation. Punch in 1.05, hit the exponent key, then 14 equals, and then times 20. All right, and we find the value to be approximately 39.599. Here's another one. Now, this one involves fractions, and we may be told here, let's presume that we're told that it's a geometric sequence, and we want to find a particular item, a sub 8. Now, what's not clear here, perhaps, is the value for r, the common ratio. What are we multiplying by to get the succeeding terms here? Now, we can kind of use trial and error to see through it, or we can use another kind of technique. Now, we know this much, though. We know that a sub 1 is negative 1/3. Okay, good. Now, what about the ratio? The common ratio is the ratio of succeeding terms. That is, I could take something like, a sub 3 and divide by a sub 2 to find that common ratio. Let's do that here. This is, let's see, a sub 3 is negative 1/27, and a sub 2 is 1/9. So I could make this calculation, you see. Now, it's a complex fraction, and we know that it's negative 1/27 divided by 1/9, which means negative 1/27 times 9/1. Oh, happy day, we have a cancellation. The 9 and the 9, 1, 9 and the 27, 3. So we get negative 1/3 for the common ratio. So that's the way to make the calculation if we're ever confused. Okay, negative 1/3 then is the common ratio. So we can write the expression for the nth term. The nth term is first term times r to the n minus 1. And away we go to find the 8th term, a sub 8. And we have all of the information we need. Let's see, the first term from right here is 1/3. The common ratio is negative 1/3. Excuse me, the first term is negative 1/3. My bad. Common ratio is negative 1/3, and we want the n minus 1. Well, that's 8 minus 1. You see, we want the 8th term, so it would be 8 minus 1, which is 7. So we have a sub 8 then is negative 1/3 times negative 1/3 to the 7th. But if these two are alike, then I have like bases. I can add the exponents. The exponent here is understood to be 1. So we could write this as negative 1/3 to the 8th power. And there are other ways to manipulate this as well. I mean, we could pop it into the calculator right now, but just realize that there are a lot of ways to manipulate fractions raised to exponents like this. I'm noticing, first of all, that I've got an even exponent on a negative number. That's going to make this value positive. So I can eliminate the negative sign right away. I could also apply this exponent to numerator and denominator separately, and I could think of this as 1/3 to the 8th power if I wanted to. Now, it's important to realize these different manipulations because you may have an answer in the back of your textbook that is some variation on this manipulation, and you have to be able to recognize whether or not you have correct answers or not. And by the way, 3 to the 8th power is 6,561, so you might see that in this denominator. And if we wanted a decimal approximation, we could pump it into the calculator. Suppose we know that a sub 2 is 3 and a sub 5 is this fraction. We want to find a sub 1, and maybe the problem would ask to find a sub 20 or something else here. But regardless, we always start problems like this in pretty much the same way. We take this model for the nth term of a geometric sequence, and presumably we would be told that it was geometric here. But we would start with that notion. We would say, okay, the nth term is a sub 1 times r to the n minus 1, and just put in information that we know. We have information about a sub 2 being 3, but we know this. If this is a sub 2, then we have a sub 1 times r. We don't know either one of these, but n minus 1 is a correspondence here with this n. This is the n we're talking about. So if 2 is n, then this would be 2 minus 1 or simply 1. I'm not going to write the 1 here, but it's just a sub 1 times r. And we're given the information about the value of a sub 2. It's 3. So this is 3 equals a sub 1 r. That's all that we know so far about this. Now, what information do we have knowing that a sub 5 is that fraction? Well, in a similar way to this situation, if a sub 5 is 3/64, and we know a sub 5 is found by taking a sub 1 and using the common ratio as a factor 5 minus 1 or 4 times. We're given the value of a sub 5 as 3/64. And away we go. Now, away we go. Where are we going? Well, let's see. We have a couple of equations here involving a couple of unknowns, the a sub 1 and the r. So 2 equations and 2 unknowns, we ought to be able to solve this system of equations. And we can do that by just finding or solving for one letter in one equation and putting the information into the other equation. That's by substitution. So it's pretty easy here to solve for a sub 1. If I do that, I get 3 over r equals a sub 1. Notice I'm just dividing on both sides by r. All right. With this information, I pop it into the other equation. If a sub 1 is this fraction, then I have 3/64 equals this fraction times r to the 4th. Oh, good. The r's can cancel here. I've got 3/64 then. Whoops, 3/64 equals 1 factor of r cancels up here. So we have 3r to the 3rd. And now I can divide on both sides by 3. If I divide on both sides by 3, I get, well, let's come up here. Dividing over here by 3, I get 1/64. And on the right, when I divide by 3, I have r cubed. Now, using this multiple root property, I can take sort of the cube root on both sides. I find 1/4 then to be equal to r. Well, if r is 1/4, then I can find the other variable, the a sub 1, by using this information back over here. We know that a sub 1 is 3 over r. Now, I could use the information here. I could use it here. I could use it over here if I wanted to. But at any rate, I just plug that back into some form that has both variables in it. And this is pretty easy to plug into. This is 3 over, let's see, r was 1/4. Now, 3 divided by 1/4 is 3 times 4 over 1. 3 times 4 over 1, oh, that's 12. So a sub 1 is 12. Now, it turns out that this is what I was looking for. I was looking for the value of a sub 1 in this problem. If I wanted to answer other questions about this problem, then I would generate the form, you see, from the model. I would generate this form by using the value for a sub 1 and r. I would do this. I would say, okay, a sub n, I know, is a sub 1 times r to the n minus 1. And I found the value of a sub 1 to be 12. And I found the value of r to be 1/4. You see, and then using this, we can generate any term in our geometric sequence. Up to this point, we have talked about 3 different mathematical models, 3 formulas dealing with arithmetic and geometric sequences. Let's review the 3. Now, 2 of them have to do with finding the nth term. The nth term in an arithmetic sequence is found by a sub n is a sub 1 plus n minus 1 times the common difference. For geometric sequences, it's a sub 1 times the common ratio raised to the n minus 1 power. We also talked about finding the sum of n terms in arithmetic sequences. And the sum of n terms in arithmetic sequences we designated as s subscript n. And it was n over 2 times a sub 1 plus a sub n. Now, to fill in all of the formulas here, we need the sum of n terms involved in a geometric sequence, and here is that formula. Now, I'm just giving it to you here because I don't have a handy memory crutch for this kind of equation. There's just no handy development of the formula and that kind of thing to help you remember it. I do want to point something out, though. The numerator and denominator of this fraction are very similar to one another. And this exponent n that's on the common ratio r is inside this outside parenthesis. It's And a common mistake is to put it outside. All right, so that's one thing to be careful about. Also, it's possible to write this fraction with the terms in the opposite order. That is, we could write this as r to the n. Here, I'll show you. I could write this as r to the n minus 1 over r minus 1. This is just a variation on the same idea. Okay, here's a problem. Suppose we want to add these items. Now, first of all, we established that we're dealing with a geometric kind of sequence, and therefore this is a geometric series. But we can see that clearly by noticing that successive items are generated by multiplication of the same item. And 1 times 3 is 3, times 3 is 9, times 3 is 27, times 3, and so on. Okay, so it's geometric in nature. Now, one thing that might have to occur in situations where you're given the items being added is sometimes the nature of the question will cause you to have to generate the expression for the nth term. And here then we might apply that. We don't really have to do that in this case, but I just want to show it to you. So it's a sub n times the first term times the common ratio to the n minus 1. A sub 1 is 1, common ratio 3 to the n minus 1. Now, using this expression, we could actually write the request for summation using the summation notation. You see, it could go something like this. I'll let K be the counting mechanism on the index. And let's say we're going from 1 to, let's see, 1, 2, 4, 6. 1 to 6. We have 6 items, you see. And it's 3 to the n minus 1. Now let's see if this isn't the case. If k is 1, we have 1 minus 1, 0. 3 to the 0 is 1. That's the first item. If k is 2, we have 2 minus 1, 1. 3 to the 1 is 3. That's the next item. Okay, so it seems to be working out just fine. All right, now, so with this, then, we can identify all the elements necessary to find the sum. So it's the sum of n items in a geometric sequence is the first item times this strange looking fraction, 1 minus r to the n over 1 minus r. You see, and now we just identify the elements that we need and go about our business. A sub 1 is 1, and then 1 minus, common ratio is 3, to the n. The number of items being added here, it was 6. 1 minus 3, and away we go. Let's see, we have 1 minus 3 to the 6th power. Big number. We have, I'm just going to leave it in this form. This 1 minus 3 is negative 2. And now we perform the calculations, presumably with the calculator here, and we find that sum to be, now notice that this is going to be a negative numerator and a negative denominator. The value is going to be positive, which we would expect here by adding all of these positive numbers. But it turns out to be 364. A more common way to request summation is using the summation notation. We recognize this as the sum of a geometric sequence because we have a counting mechanism in the exponent, and the base of the exponent is our common ratio. Now, in circumstances like this, it might be handy to generate the first few terms that are being added just as a kind of a check to see if the summation that we come up with is a plausible one. I'm not going to do this here, but it's just something that you might think about in the future. All right, we can jump right into our equation here. The sum of n terms is the first term times that strange fraction, 1 minus r to the n, over 1 minus r. R is the common ratio, and we know it to be 1/4. So we just pop in information. Now, a sub 1, the first item, when I is 1, we have 1 minus 1, 0. 1/4 to the 0 power is 1, so 8 is a sub 1. And then we have 1 minus, common ratio is 1/4. And 1/4 is to the n power. Now, how many items do we have? Well, we're going from 1 to 10, so we have 10 items. And this is all over 1 minus 1/4. And now I think it's a matter of punching the calculator. Just be careful when using the calculator here to have enough parentheses involved to contain this numerator and this denominator sort of separately, and you need parentheses for the overall fraction as well. So a lot of parentheses need to be in here. And to avoid the parenthesis that might be thought of as necessary right here, you might use 0.25 for 1/4. At any rate, when we find this sum, it turns out to be, I should say, approximately 10.67. Here's another one. Now notice that the counting mechanism is going from 0 to 15. We see that the counting mechanism is an exponent or part of an exponent. It is the exponent here. But if it's either part of or in the exponent, then we know we have a geometric situation. And the base of the counting mechanism, the 4/3 here, is the common ratio. So again, we jump right into our formula and replace within it. Now, a sub 1, when n is 0, you see we have 0 here, this becomes 1, we have simply 2 for a sub 1. 1 minus r to the n. Well, let's see. The common ratio is the base of the counting mechanism. That's 4/3. N, the number of items being added. Now, be cautious here. The tendency is to just look at the upper limit in this notation and say that it's that amount. It's 15 here. But it really isn't because we're starting at 0. So the number of items being added is really 16. All right, now once again we jump into the calculator. Now, there is a tendency sometimes when fractions are involved to round the fractions early in the problem, and I caution you not to do that. In the previous problem, we could change the fraction to a decimal. It was 0.25 exactly. Now here, if we took 4/3 and thought of it as, we think of this as 1 1/3, we might say, oh, 1.33 is close enough, and we raise it to the 16th power. Well, it turns out that that error that is created by approximating this, the decimal is going to create an error in the answer. So don't do that. Use an exact value here and introduce the appropriate parenthesis to accommodate that. At any rate, that sum turns out to be 592.65. Now, this is a large value mainly because the common ratio is a number larger than 1. And really, any time that common ratio is larger than 1, and you're adding a lot of things, then the number, it tends to be pretty large. Now, let's talk about the notion that we're adding many, many things. We want that number of items to be added to approach infinity, and to be infinity here in our next example. It turns out that looking at the common ratio is very important in circumstances like that. That if the common ratio is a number larger than 1 or smaller than -1, that the sum will go out of sight. It's boundless. All right? But on the other hand, if that common ratio is a number between -1 and 1, but not 0, it's just a common fraction, you see, either positive or negative, that its value will become 0. Let me show you what I'm talking about. That is, when we use this formula and the ratio is raised to the nth power, that when n gets really, really big, if the base of that exponent is between, let's say, 0 and 1, just for conversation now, it's just a common fraction raised to a very big exponent, this value goes out. You see, it approaches 0, and when that's infinity, it is 0. So the nature of this equation changes somewhat when we're talking about adding an infinite number of items. And when we're adding an infinite number of items, this term goes out. This becomes 1 over 1 minus r. So we could write this as a sub 1 over 1 minus r. All right, so this is what we use when we're adding an infinite number of items in this environment, when we're talking about a geometric sequence. So we're adding an infinite number of items in a geometric sequence. It is a geometric series, and the request would be made like this: as n runs from 0 to infinity of some kind of expression. We see the exponent is the counting mechanism, and the base of that counting mechanism is our common ratio. Now, to generate a few of the items that are being added here, if n is 0, then our first item is 4. If n is 1, then we have 1/4 times 4, or 1. If n is 2, we have 1/4 squared. You know, another way to do that, though, is to just say, gee, if the common ratio is 1/4, let's just generate succeeding items by multiplying by 1/4. The first item is 4. 1/4 of 4, that's 1. 1/4 of 1, that's 1/4. 1/4 of 1/4, that's 1/16. You see, doing it like that is a little easier than using the model up here, it turns out. Well, let's see. To go through with our formula, it's a sub 1 over 1 minus r, and a sub 1 turns out to be 4, and then 1 minus r is 1 minus 1/4. That's 3/4 in the denominator, and so cleaning this up a little bit, it's 16 over 3, or 5 1/3. I think it's kind of interesting that when the common ratio is a number between -1 and 1, but not 0, that we can make this calculation, and it's often the case that the sum is a specific number. All right, that's an important idea. Here's a problem involving a finite geometric series.
A deposit of $50 is made at the beginning of each month for 5 years in an account that pays 5% compounded monthly. What is the balance A in the account at the end of 5 years? Well, we know that our formula for figuring this sort of thing, that is the amount in an account at the end of a certain period for a particular investment, is this: P times 1 plus R over N to the NT power. Well, we're going to have to use this formula a number of times, aren't we? After all, each deposit is earning interest for a different period of time. In month 1, we have a $50 deposit which earns interest for the entire 60-month period. In month 2, we have a $50 deposit which earns interest for 59 months. And we go all the way down to the last month when we make a $50 deposit, and it earns interest for only 1 month. Let's look at the situation algebraically. In month 1, the deposit is $50, so that's the principal amount of investment. The rate is 5%, or 5/100ths. N, the number of compoundings per year, is 12. And T, the time, is 5 years. Now that time T is the item that changes from month to month. But for the first month, the time is the entire 5-year period. Now notice 5 times 12 is 60. So our first investment is earning interest for 60 months. On the other hand, our investment in month 2 is earning interest for only 59 months. And then the next one would be 58, and so on down to month 60, in which our investment of $50 is earning interest for only 1 month. Well, notice we have an interesting sequence here. And our counting mechanism can be thought like this. Instead of writing this as with our exponential counting mechanism as 60, 59, 58, all the way down to 1, let's rewrite in a more logical order. In the 1, 2, 3, 4, you see the more logical counting order like this. Well, writing it like this, we see that we have the sum of a geometric sequence. And we can write that sequence like this: the summation, as n runs from 1 to 60, of 50 times 1 plus 5/100ths over 12 to the n power, where n now is our counting mechanism. Our formula for figuring the sum in this situation is this. Now, a sub 1 is the first item in the sequence, and it is found by replacing n with 1. So a then becomes simply 50 times 1 plus 5/100ths over 12. Now in the bracket, the r value is simply the base of our counting mechanism. So in this case, r is 1 plus 5/100ths over 12. Now notice the n. Now the n involved here is, in the formula, is the number of items we're counting. And in the equation above, the n stood for the counting mechanism. Now this seems to be confusing, but I've set it up so that both of these are lettered n, just to point out the difference between the two and the possible confusion that can occur. The n in the A formula is simply a counting mechanism, and the n involved in our formula for figuring the sum of the geometric sequence is the number of items being counted. And that number of items here, of course, is 60. Okay, so n is replaced with 60 in our formula. Now the r down below is the same as the r above. It's the base of the counting mechanism, 1 plus 5/100 over 12. Now we simply go through and perform the indicated operations by punching our calculator a bit, and we find A to be approximately 3,414 and 47/100ths, which we interpret in dollars and cents and write our answer. The balance in the account at the end of 5 years is $3,414.47.